Next, I want to start talking about colligative properties. So colligative properties are the effect that solutes have on the physical properties of solutions. What we're going to find out is that for colligative properties, all it matters is how many of the solute molecules we added to the solution, right? Colligative properties are things like vapor pressure reduction, freezing point depression, boiling point elevation, and osmosis. So when I dissolve something in solution, I'm going to increase its boiling point. And here's the thing. It doesn't matter what I dissolve into it. It just matters how many particles I dissolved into it. So if I dissolve sugar, if I dissolve 10 sugars molecules into a solution, I'm going to increase its boiling point. If I dissolve 10 sodium chloride molecules or formula units, I'm going to increase its boiling point twice as much as I did for the sugar. Now you just said, well, it mattered on how many particles, right? And I just added 10 particles of sugar and I added 10 particles of sodium chloride, but I told you that the sodium chloride is going to double that increase in the boiling point. Can anybody tell me why that would be true? If all that it matters is the number of particles, and I added 10 sugars and 10 sodium chlorides, why did sodium chloride have twice the effect? Because when the sodium chloride dissolved into water, it was a strong electrolyte, and it dissociated into a sodium ion and a chloride ion. So now I have 10 sodium ions and 10 chloride ions. I have 20 particles. That's twice the number of the 10 sugar molecules, which were non-electrolytes and did not dissociate at all. So colligative properties affect the physical properties by just the number of particles added, not whether the particles are one type of molecule or another, whether they're an ion or a neutral molecule, doesn't matter. It just matters how many, okay? So let's talk about the vapor pressure of a solution. So the vapor pressure of a volatile solute. Now, volatile simply means that it easily evaporates. We would consider water to be volatile. If I set a glass of water on my desk and I come back the next day, there'll be a measurable amount of that water gone. It will have evaporated. And we're going to compare that to non-volatile solutes. Non-volatile solutes, so for example, let's say sodium chloride, table salt. If I set a cup of table salt on my desk and I come back tomorrow, if I come back a year from now, I will not be able to determine any discernible difference in the volume of that sodium chloride. So that's what we consider a non-volatile solute. So basically, it will evaporate, it's volatile. If it does not evaporate, it's non-volatile. Okay? So the vapor pressure is going to be changed, and it's going to depend on whether the solute is volatile or non-volatile. Okay? So we're going to have two different equations depending on whether or not the solute is volatile or non-volatile. So vapor pressure lowering, again, it's a colligative property. It's equal to the vapor pressure of the pure solvent minus the vapor pressure of the solution. Okay, now that's a little confusing, and I'm going to come back to an equation that clears that up. So Raoul observed that the vapor pressure of a solution depended on the mole fraction of the solvent. So in the case of vapor pressure, the units, the concentration that we need is mole fraction. We're going to find out for each one of these colligative properties, we need to use a different type of concentration. So in the case of vapor pressure lowering, that concentration is mole fraction. And basically he found this. Now this is for a non-volatile solute. So again, this is the solute that will not evaporate. It won't vaporize, okay? If we have a solution, the vapor pressure of the solution is going to be the vapor pressure of the pure solvent. So that's what the little knot here is. right? That just means it's the pure solvent times the mole fraction of the solvent. So again, the vapor pressure of the solution is going to be equal to the vapor pressure of the pure solvent times the mole fraction of the solvent. Okay. Now, if we have a volatile solute, actually, I think I'm going to go into Y here. And if it's the change in, you could just do some manipulation with this equation here for a before and after. And what you get is that the change in the vapor pressure of the solution then is just equal to the vapor pressure of the pure solvent times the mole fraction of the solute. Okay, so notice this is solvent and this is solute. So if you're trying to calculate the vapor pressure of the solution itself, you're going to be using the solvent mole fraction. But if you're trying to determine the change in the vapor pressure, then you're using the mole fraction of the solute. Okay? So make sure you're solving for what you're looking for. Usually, it is this guy. Oh, by the way, I'm sorry. I keep forgetting that I haven't had all of you for Chem 110 and you're unfamiliar with this. Anytime you see a blue bubble like this, you should be memorizing those equations. Okay? Now, I know, unfortunately, because this is the Zoom class, that a lot of you are not going to bother to memorize these equations, and you're going to make a cheat sheet that you're going to use while you're taking the exam because I can't see it. That's fine. I can tell you this, though, you're probably going to do worse on the exam than if you had memorized the equations. That has been my experience for teaching now for 17 years. I used to allow students to have, well, I didn't allow students to have equation sheets at first because my colleagues said that you shouldn't allow them to have them. And then I was like, well, what the hell is the difference? I'll just let you have equation sheets. My average student scores dropped by nearly 10%. That's a letter grade, okay? So again, I strongly encourage you to memorize these equations. And there's reasons behind that. A lot of students will do very few homework problems. All of a sudden, well, I can just cheat and use my equation sheet. I don't need to do any homework problems. They get to it. Number one, they don't even know what the variables represent. They don't know what the P, this little not solvent means because they haven't done their homework problems and they don't even recognize them. And then a lot of times in chemistry, you have to convert one thing to another. Well, without practice, you're not going to do that very proficiently. It's going to take you a lot longer to answer the questions. You're going to run out of time. You're going to tell me that my exam was too long, and I'm going to tell you, no, you were wrong. You just didn't do what you were supposed to do. Okay? So keep that in mind. You should really memorize those equations that are in these blue bubbles. Okay. So let me give you a little demonstration of how this vapor pressure lowering works. And this is actually a really cool experiment. If you could do it on your own, you'd need what's called a bell jar. Okay, so it's just a big glass jar. It's open on the bottom, and then there is usually a glass or marble piece of flat piece, and they fit very tightly to one another. So it's basically an airtight seal, so gas molecules can't get in or out of this bell jar. And if you take two beakers, and you take and add, let's say we have 100 milliliters of water in each beaker, and I put 1 gram of sodium chloride in this one, and I put, let's say, 2 grams of sodium chloride in this guy over here. So B then is much more concentrated than A. Well, according to Raoult's law, with a non-volatile solute, because this guy has more solvent molecules than this guy is going to have a higher vapor pressure. And remember what vapor pressure is from Chem 110. That's the amount of molecules escaping into the vapor. Now, remember, it's just going to be the solvent because the solute's non-volatile. The salt concentrate, the number, let me rephrase that, the number of salt molecules in these beakers is never going to change. Right? Because the salt's not going to evaporate. So the number of sodium chloride molecules are never going to change inside the two beakers. But the vapor pressure of this one, because again, vapor pressure is dependent on the mole fraction of the solvent. And because the mole fraction of the solvent is greater in A than it is in B, the vapor pressure of A, the amount of water molecules that are escaping compared to coming back in, is higher than this one over here. Well, that means this guy's evaporating faster and having the water molecules come in slower. And this one's going out slower. So over time, what happens again, for this one here, a lot more molecules are escaping out compared to the molecules coming in. And for this one here, again, less molecules escaping out than are coming in compared to A. And so over time, what happens is that the molecules, again, remember, it's a dynamic process, but because these were escaping faster than these, now all of a sudden, over time, the levels of the two change. And because I had double the amount of salt in this guy here, well, now this solution, the water molecules basically escaped from here to here. Now A and B are the same concentration, and their vapor pressures are now the same. So this is the way Raoul actually demonstrated that it depended on mole fraction. He did the experiments and then analyzed the data and realized that it was the mole fraction that determined what the vapor pressure of the solution was going to be by this experiment right here. This was for a non-volatile solid. Now he did similar experiments for volatile solids. So this is, again, this time the solute itself would evaporate. So for example, if I make a solution of ethanol in water, and ethanol is my solute, well, pure alcohol, pure ethanol will evaporate. In fact, evaporates quicker than water. So it's a very volatile solute. And so for volatile solutes, the pressure of the solution, the mixture, is got to be the sum of the vapor pressure of both the solute and solvent. And again, the individual vapor pressures of the solute and the solvent are going to be dependent on their mole fraction. So the vapor pressure of the salt solution is going to be the sum of the vapor pressure of the pure solvent times the mole fraction of the solvent, plus the vapor pressure of the pure solute, which would be the ethanol in my example, and the mole fraction of the solute, which again would be the ethanol in my example. So there it is. So this is the equation for a volatile solute. So we have two Raoult law equations, one for a non-volatile solute, which basically was just this first part right here, right? And then if we had a volatile solute, we had to add this additional part to account for the vapor pressure of the volatile solute. Okay, any questions? And so, excuse me. And so the Van Hoff factor, so again, coming back to colligative properties. So as I said, colligative properties depend on the number of particles, the number of solute particles in solution, not on their properties. So it doesn't matter what the chemical is. It doesn't matter if it's a neutral or an ion, just how many of those solute particles are actually in solution. Okay, so that's what these colligative properties depend on. So an example, as we've already discussed, is lowering the freezing point of water when salt's added. That's why we throw salt on ice in the wintertime, because the salt literally lowers the temperature of the water, and now it's going to freeze at a lower temperature. That's why when it gets really, really cold, they don't even put salt on the roads anymore. They'll put sand down, because the salt lowers the melting temperature so much, but if it's really, really cold, the salt isn't going to melt the ice. So then they just throw sand down so that at least the snow or the ice has some grip to it, okay? So the vapor pressure, same thing. When you throw a non-volatile substance into a liquid, it's going to lower the vapor pressure. And we'll talk about why that happens here in a little while. But like I said, each one of these depends on the number of particles in which of the solute that there are in the solution. So for molecular compounds that just, dissolve and form individual molecules, well, that's just one molecule per particle. But for things that dissociate, ionic compounds, well, for example, sodium chloride, you throw it in water, it dissociates into a sodium ion and a chloride ion. So that one sodium chloride that you throw in there is now two particles. And that's what the Van Hoff factor is. Moles of particles in solution versus the moles that you actually dissolved. So if I dissolved 1 mole of sodium chloride in water, I know that I'm going to have 2 moles of particles, 1 mole of sodium and 1 mole of chloride. So that's 2 moles. And so that's what the Van Hoff factor is, I. Okay? So for non-electrolytes, like I said, like for example, sugar, throw it in water, it does dissolve, it's soluble, and the solid falls apart into the individual sugar molecules, but the sugar molecules themselves stay intact. And so the Van Hoff factor for sugar would be 1. Okay? For strong electrolytes, simply depends on how many particles or how many ions that ionic compound is composed of. So for strong electrolytes, I is going to be 2 or more. Okay. So for example, sodium chloride is going to have, without looking at your notes, sodium chloride is going to have what value of I? When I throw sodium chloride into water, what happens to it?
Sodium chloride dissociates into a sodium ion and then a chloride ion.
So how many ions is that?
2.
2. So I is equal to 2. Okay, what about the aluminum sulfate? So this comes back to naming compounds again. And you're going to hear me say this over and over and over throughout this course. If you don't know how to name compounds, you really need to go back and learn how to name compounds. Okay? Because the first thing you're going to ask yourself, is this thing ionic or molecular? These are the questions you ask yourself when you're naming a compound. Is this thing ionic or molecular? What do you think? Ionic or molecular?
Would it be ionic because the SO4 is a polyatomic ion?
Yeah, right. We have a metal and a polyatomic ion. So if we have a metal and a non-metal, like this here, it's ionic. Or if we have a polyatomic ion anywhere in it, so that's another reason you got to know your polyatomic ions. You got to be able to recognize them when you see a chemical formula. So you got to know how to name compounds, and part of that is knowing your polyatomic ions. Okay, so yes, this thing is ionic. So Keenan, then what's the I value going to be for aluminum sulfate?
Would it be 5?
Absolutely.
Okay.
It's going to, and again, this is being able to write your molecular to your complete ionic to your net ionic equation, which again is going to be critical in this course, because you should be able to recognize this. This is going to dissociate into 2 aluminum 3 plus and 3 SO4 2 minus. Well, that's 2 aluminum and 3 sulfate. That's a total of 5 particles. So for aluminum sulfate, a strong electrolyte, right? That's going to be the other thing too. Is this a strong electrolyte? The answer there is yes. Rule number 4 of your solubility rule says that most sulfates are soluble, and for salts, and again, this is only for salts and hydroxide bases, a soluble salt is a strong electrolyte. Sugar's soluble, but it's not a strong electrolyte. But when you're dealing with the solubility rules, soluble means, yes, it dissolves in water, but it also means it's a strong electrolyte. Now, the exceptions, of course, to the sulfates are silver, mercury, lead, and calcium, strontium, and barium. You should know those solubility rules already. Again, they're posted on Canvas of the tables that you must know. So that's 5 particles. Okay. Okay, what about the lithium phosphate? Ionic or molecular? Kayla, what do you think?
It's ionic.
Absolutely, right? We have a metal and a polyatomic ion. Is this a strong electrolyte?
Yes.
Yeah, group 1A metal, right? Lithium is in a group 1A. So that's rule number 1. So yes, this is a soluble salt. Okay, Kayla, last thing. What is I?
7 is 4 plus 3.
Okay, tell me what ions. If I was going from the molecular equation when it looked like this, how would you write it in the complete ionic equation? Since this is a strong electrolyte, it's going to dissociate into its individual ions. What would you write in the complete ionic equation?
Well, 3 ions for lithium,
The 3 Li plus,
3 Li plus ions,
okay?
and oh wait, sorry, and 1 PO4
3
ion.
minus,
3
right?
minus, yeah.
What is I?
So it's 4. Sorry, not
You
7.
get it? So knowing how to name your compounds, knowing how to write molecular complete ionic equations makes determining I easy. Okay, so yeah, it's going to be 4. There's 3 lithium ions and 1 polyatomic phosphate PO43 minus ion. Okay, any questions on this so far? For weak electrolytes, which by the way, I'm not going to make you deal with, I is some non-whole number because only some of that ionic compound dissociates. So I, in most cases, is much, much less than 1. So thrown in a grain of a insoluble salt, well, that's just 1 grain. Now it's composed of a whole bunch, billions and trillions of ions, but they're not even separating into individual ion pairs. Only a couple of the actual ions are coming off that solid chunk. So the I value is much, much less than 1. We're not going to deal with that. Okay. Okay, so let's talk about some of these colligative properties like boiling point elevation. So now we know that the normal boiling point of a solution is the vapor pressure of the solution when it, so the boiling point is when the vapor pressure of the solution is equal to the external pressure. The normal boiling point is when, if you were boiling water at the beach, okay, that's when the vapor pressure of the solution is now equal to the external. So if you're at the beach, that's 1 atmosphere, the water is going to boil at 100 degrees Celsius. Okay. Now the boiling point, now we're always going to deal with a normal boiling point, but keep in mind again, the reality is the boiling point here in Western Pennsylvania, where we have a normal barometric pressure of around 740 millimeters of mercury rather than 760, water boils at a lower temperature here than it would at the beach. Okay, but we're not going to deal with that. We're going to always assume the normal boiling point. So we're going to assume that we're always living on the beach. Okay. Okay. Now, because the vapor pressure is reduced in the presence of a non-volatile solute, we've already seen that with Raoult's law for non-volatile solutes. So a greater temperature then must be reached to achieve boiling. Okay. So let's go back to phase diagrams. So you guys remember phase diagrams, right? We have the temperature versus pressure. And then these boundaries represent, like going from this solid to the gas would be sublimation. Going from the gas to the solid would be deposition. Going from the liquid to the gas would be boiling or evaporation. And going from the gas to the liquid would be condensation. Going from the liquid to the solid would be freezing. Going from the solid to the liquid would be melting. So that's our phase diagram. So what happens here is this line represents the pure solvent vapor pressure. So we're talking about just the pure solvent here. And then this would be the solid vapor pressure, which we're not going to deal with right now. So this is the pure solvent vapor pressure. So we can see that the vapor pressure is increasing with temperature, exactly what we expect, right? The vapor pressure always increases with temperature. Okay, if I add something to it, it makes it changes the phase diagram. This line shifts down to here, and this line shifts to here. Okay, so now we can see that for this thing to boil at the same temperature, so let's say we're staying at the same temperature, we can see that there's a difference then going across. So here was the boiling point before we added anything. Here's the boiling point after. So you can see that we have a change. We have an increase. So we increased the boiling point. This is the change in that boiling point. We increased the boiling point by adding something to it. Okay? So we could actually quantify that using this equation here. So the change in the boiling point is going to be equal to the Van Hoff factor. This proportionality constant, which we call the boiling point elevation constant, okay? Now that is only dependent on the solvent. It doesn't matter what the solute is. That is only dependent on the solvent. And you'd simply look that up in a table. So in the tables of chemical data posted on Canvas. And then this is the mole concentration, the mole concentration. So that's going to be the moles of solute divided by the kilograms of solvent. That's the mole concentration, okay? And again, you can get the boiling point elevation constant from the tables of chemical data posted on Canvas. Now, we're also going to lower the freezing point. We can see that again here, right? So here we can see that the freezing point of the pure solvent is right here. But once we add something to the solution, we see that the phase diagram changes, and now the new freezing point is here. So we can see that we lowered the freezing point this time. We lowered it this time, okay? And again, we can quantify that by using this expression right here. Again, this is the change in the freezing point. Now, I believe your book does not include a negative sign in its equations, so be careful. Sometimes my equations are slightly different than the books whenever it deals with del T, because to me, del T always means the same thing. It's the final temperature minus the initial temperature. The book is just assuming that you know the freezing point depression value has to be negative. I'm building it right into the equation. The freezing point depression is the change in the freezing point is negative. Again, times the Van Hoff factor. Now this is the freezing point depression constant. Again, that is unique for each solvent. Doesn't matter what the solute is. It's unique for each solvent. And again, you're going to find those in the tables of chemical data or in the appendix of your TRO text for each individual solvent. And again, we're going to multiply that by the mole concentration, the moles of solute per kilogram. I'm sorry, the moles of solute per kilogram of solvent. Okay. Okay, let's try an example of that then. I want to know, what are the boiling point and freezing point of an aqueous solution that is 0.88 mole glucose? Okay. So, well, we know that the equation for the change in the boiling point is the Van Hoff factor times the boiling point elevation constant times the mole concentration. The mole concentration was already given to me. Let's see, who haven't I picked on? Kaylee, what is the Van Hoff factor for glucose? Again, the first question you should ask yourself, is glucose molecular or ionic?
Is it molecular?
Okay, so a molecular compound contains nothing but nonmetals, but we got to be careful because what about NH4 Cl? Is that molecular or ionic? NH4Cl. That contains nothing but nonmetals.
That would be ionic.
Why would it be ionic if it contains all nonmetals?
Because of NH4.
NH4 is a polyatomic ion, right? It's NH4 plus and Cl minus. So again, that's why you got to know your polyatomic ions. Are there any polyatomic ions in this?
No.
No, but again, I'm only asking you to know the polyatomic ions listed on those tables that you must know. Put them on cue cards. I'm telling you, it will not be that hard to learn them. Okay? You just got to try a little. Okay? So yes, this thing is molecular. Therefore, what is I, the Van Hoff factor? Is it a strong electrolyte? Well, remember, with the exception of organic acids, all molecular compounds are non-electrolytes. They don't dissociate at all. So therefore, what is the Van Hoff factor for glucose? It's going to be 1, right? Each glucose molecule is its own glucose molecule.
Oh, okay.
So in this case, the Van Hoff factor for glucose is simply going to be 1. It's a molecular compound. It's a non-electrolyte. So it'll just be 1. Is everybody clear with that and understand how we deduced that? We came to that conclusion. Okay. Okay, now we're simply going to look up the values for the boiling point elevation constant and the freezing point depression constant, might as well, because we're looking for both. And when we look that up in a table, the boiling point elevation constant is 0.512 degrees Celsius per mol. That could also be given as degrees Celsius times kilograms divided by moles, since mol is moles divided by kilograms. And then the freezing point depression constant and again, these are for water. These are for water because this is an aqueous solution and we don't care about the solute. All we care about is the solvent. So this is water. And so for water, the freezing point depression constant is 1.86 degrees Celsius per mol. Okay, so we looked that up. So now we know that. We know the mol concentration. We know I. So now we can determine that the change in the boiling point is 0.45 degrees Celsius. Okay. Freezing point depression, same thing. I is going to be the same number. We now have the negative out front. We looked up Kf when we looked up Kb, so we know it's 1.86, and the mol concentration was given to 0.88. So that is negative 1.63 degrees Celsius. Okay, so let's see. Taylor, what is the boiling point of this 0.88 mol glucose solution? What is the boiling point of it?
Is it just 0.450 degrees Celsius?
Okay, what's the boiling point of water? These are the only boiling point and freezing point that I expect you to know is for water. I will give you the boiling point and melting point for any other substance except for water. So in degrees Celsius, what does water boil at?
I'm not sure that I remember.
What does it freeze at?
32 degrees.
That's Fahrenheit.
Well,
Celsius, what does it freeze at? It's easy. That's why we like the metric system. Take a wild guess. What does water freeze at in degrees Celsius?
is it at 0?
Yeah. And what does it boil at? Really easy. What is it?
I'm not sure.
100.
Oh.
Okay, it's easy. I'm telling you, it's easy. Okay, so let me re-ask that question then. What temperature is this 0.88 mol glucose solution going to boil at while we're boiling it while we're sitting at the beach?
100?
That's pure water, but we added sugar to this water.
So it would be higher than 100?
Exactly what would it be? We just calculated the change in that boiling point.
Oh, would it be 100.450?
Exactly. And what is its new freezing point going to be?
100 minus
What does water freeze at?
0.
And so the change in, what is the new freezing point of water?
Would it just be negative 1.63?
Exactly, right? So again, remember, these del's mean final minus initial. So the initial would have been the initial melting point and boiling point of the pure solvent. We now want the final, which is now going to be the new boiling point and melting point of the solution, okay? So we would simply rearrange that. And again, we would have to add that to the 100. And so that would be 100.45 degrees Celsius for the new boiling point. And the new freezing point would be negative 1.6 degrees Celsius. Any questions on that?
Is the freezing point always going to be a negative?
Absolutely.
Okay. All right. That's good.
Oh, wait. Are you saying the new freezing point is always going to be negative?
No, I just mean the value that you
The
calculate.
change in will always be negative.
Okay.
The new freezing point won't necessarily be negative. If the initial freezing point was well above 0 degrees Celsius, it's just going to be a lesser value, not necessarily negative.
Yeah, okay. That makes
Okay.
sense.
Okay. Okay, let's try one more example before we quit for the day. I want to know what are the boiling and freezing point this time of an aqueous solution that's 0.88 mol calcium chloride. So again, we know, we know that we're going to use those same equations that we did. So we already know the freezing point depression constant is 1.86 and the boiling point elevation constant is 0.512 degrees Celsius per mol. But what is the Van Hoff factor? So let's see. I'm trying to pick on all of you equally. Hannah, what is the Van Hoff factor for calcium chloride?
That would be 3.
Exactly, right? And again, we got to go through the same process. We're going to look at our solute, calcium chloride. And we have to ask ourselves, is calcium chloride ionic or molecular? Well, we have a metal and a non-metal, so it must be ionic. Next question. Well, if it's ionic, is it, what type of ionic compound? Well, it's not an acid. There's no hydrogen. It's not a hydroxide. There's no hydroxide in it. It's not a metal oxide. There's no oxygen. And plus, it can only be metal and oxygen, no other non-metal. So therefore, this thing is a salt. And we could use then our solubility rules to determine whether or not this thing is a strong electrolyte or a weak electrolyte. And according to rule number, we have no rules for calcium, but according to rule number 3 of your solubility rules, most salts that contain the chloride, bromide, or iodide are soluble, except for those compounds that contain the silver, mercury, or lead ions. Those would be insoluble. Well, this isn't an exception, so that means calcium chloride is a strong electrolyte, a soluble salt and a strong electrolyte. And of course, we know that it's going to then dissociate into its 1 calcium 2+ ion, because that's a group 2A metal, and 2 of the group 7 chloride, which means it's going to be group number -8, so 7 minus 8 is -1. And so we're going to form 3 ions, 1 calcium and 2 chloride, and therefore the Van Hoff factor then is going to be 3. Okay? Okay. Okay, so, and again, we're going to look up those values for the KB and KF, which we already did, and we found them to be 0.512 and 1.86 degrees Celsius per mol. We were already given the mol concentration, so we're going to plug that in. We find the change in the boiling point is going to be 1.35 degrees Celsius. And the same thing, we're going to do the same thing as we did before with the negative IKF, the freezing point, and that's going to give us negative 4.91. So we can see that and then of course we're going to add this to 100 because again, we're looking for the final. The initial is 100. So we would then add that 100 to the other side. So 100 plus 1.35 is 1.4, okay, would be the new boiling point. And then again, the initial this time is 0, so that just cancels out. So the new melting point is just going to be the negative 4.9 degrees Celsius. So we could see from the previous slide that just with the sugar, the boiling point was just 100.45. Now it's a degree higher. It's 3 times higher. The change is 3 times greater, right? Because the number of particles is different for the calcium chloride than it was for that molecular glucose. Okay, any questions about any of? Okay, so last we met, we were talking about colligative properties, and colligative properties are physical properties that it doesn't matter what the particles are. Again, whether they're ionic or molecular, what type of ionic compounds they are, it just matters how many particles. Well, another colligative property is osmosis. So to understand what osmosis is, let's just take, for example, here we have a beaker, and that beaker has a screen in between it, right? So we put a screen to separate the beaker basically into 2 sections. This section has a lot of sugar molecules, so it has a higher concentration. This side has fewer sugar molecules, so it has a lower concentration. And because the screen is big enough that the sugar molecules and the solvent molecules can fit through the holes. And so this would just be regular diffusion where the molecules, and we call this a permeable membrane, permeable. So all the solute and solvent molecules can easily pass through them. And so basically just random motion, they're going to move this way sometimes, and sometimes they're going to move this way. And because all of the particles can actually move back and forth, diffusion is going to occur. And over time, we're going to get a uniform distribution of the sugar molecules throughout the solution. So we'll have a true sugar solution where if I take a certain volume here and a certain volume here, I'm going to have about the same number of sugar molecules in both. So that's just normal diffusion, okay? Now in the case of osmosis, it's different. So here's another example. So this time I have this beaker, and this beaker has a dilute sugar solution. So there's very few sugar molecules compared to water molecules. And then in this weird looking little apparatus here, I have a much more concentrated solution. So there's a lot more sugar molecules in this solution here. So there's our concentrated and our dilute solution, except this time, this is what we call a semi-permeable membrane. This membrane will only allow the solvent molecules to pass through. Now, these semi-permeable membranes can be very complicated. It could just be a size thing, right? The sugar molecules are too big to pass through, but there could also be charges. You know, you could put ionic charged groups onto this surface, or other types of functional groups on this surface that simply doesn't allow a molecule of a particular type to pass through. So these can be quite complicated. We can just think of it simply for now as that the solute molecules are too big to fit through the holes. Okay, but like I said, that is would be the simplest form, and they're usually very complicated. Okay, so this is our semi-permeable membrane. Now, we already know from other properties that if we have a concentrated solution and a dilute solution somehow in contact with one another, that the solvent molecules are going to want to go into the concentrated, from the dilute to the concentrated, until the concentration of this would equal the concentration of this, right? So the 2 solutions would have equal concentration. That's just a normal thing that occurs in nature, okay? Now, because only the solvent molecules can travel through the semi-permeable membrane, these water molecules are going to start to travel in to try to dilute this so that it's the same concentration as the original dilute solution, okay? And again, as the molecules leave here, this concentration then is becoming more concentrated. So basically what's happening is it's trying to make sure that the concentration within inside this glass thing is the same as the concentration within the beaker, okay? Now, so what's going to happen is that it's going to start to rise. Now, at some point, it's going to stop rising. And that's because gravity's trying to pull it back down. Now, there's still not equal concentrations, right? You can see that there's still not equal concentrations, but it did rise. And again, gravity's pulling it down. And so that is going to be the tug of war that occurs with osmosis. And we could actually quantify it. We could say that the height from the top of the meniscus to the surface of the fluid is going to be equal to the density of the fluid times the gravitational constant times the height. And that would be equal to the osmotic pressure. Now, we're not going to use this equation. We're going to find out that we don't need to know the density or the gravitational constant or the height rise within the fluid. We're going to do it slightly differently. So this time we have the two. So here we have our now this is just our pure solvent and this is our solution. Now again, the water molecules are going to want to flow into here and cause the rise within the tube. However, what we're going to do is we're going to apply an opposing pressure, just using some inert gas, nitrogen, argon, something. And we're going to keep applying that pressure and so that the level within the tube is equal to the level of the fluid itself. That is osmotic pressure. So that's the pressure that we're exerting to prevent osmosis from occurring. Okay, and we can quantify that. The osmotic pressure, again, given by pi, is equal to, again, this is just the Van Hoff factor. So again, that would be 1 for non-electrolytes, okay, so molecular compounds for the most part. Or if it's ionic, if it's a strong electrolyte, how many ions it dissociates into. And then this is the concentration. Now this is the molar concentration. This is moles per liter. Remember the freezing point depression, boiling point elevation was the mole concentration, but this is the molar concentration. And then this is just a molar gas constant. And since we're dealing with pressure, it's going to be the 0.082058 liters atmosphere per Kelvin per mole, right? So here's the moles per liter, right? That is the molarity. So this is going to be the molar gas constant that you use. And then T is just going to be the absolute temperature in Kelvin. Okay. Okay, just to give you an idea of how osmotic pressure would affect you. So in a normal blood cell, the concentration of salts are the same within the blood cell as they are in the fluid that's around it, the plasma. Okay, so normally that's about 0.9%. They say saline, we'll just say sodium chloride. Okay, but it's other ionic compounds as well, but it's 0.9% saline. Okay, so 0.9% some salt. Now, you could run into a situation, so in that case, the water is basically flowing into the cell at the same rate that the water is flowing out of the cell. Okay. Now, if you have hypertonic, so you have some condition in which the level of the salt outside the cell is actually higher, well, then all of a sudden, all the water wants to leave the cell to try to get the same concentration as the outside fluid. That causes the cells to literally collapse. Okay. Then there's a third possibility, which is called hypotonic. In this particular case, the salt solution outside the cell is actually less than the salt content within the cell. And so what this results in is a net flow of water into the blood cell, again, to try to get the concentration the same in and out, and that causes the red blood cells to balloon up and eventually could even burst, okay? So this is called hypotonic. Now, of course, hypertonic or hypotonic is a fatal condition. Okay, so you'd have to be very, you'd be hospitalized for that. Okay, let's talk about another very useful purpose of osmosis, and that is actually where we use reverse osmosis. In this case, we're actually applying pressure because we want to get the pure solvent. We want to separate the solutes in the solution from the solvent itself. So in this particular case, what we're going to do is we're going to apply a great pressure onto this part of the tube. That's going to force the solvent molecules out, and now we have pure water. Okay, so this is what a lot of very, arid places, they don't have a lot of rain, so not a lot of fresh water, but they might be near the ocean, a big salt body, salt water. Now, of course, you can't drink salt water, or you're going to end up with one of those, you're going to end up with this hypertonic situation, right? So this is why you can't drink salt water. You're going to raise the salinity of the fluid in your blood, and you're going to cause your blood vessels to collapse, okay? So we need fresh water, and so the way we're going to do that is we're going to take salt water, apply a tremendous amount of pressure across the semi-permeable membrane, and again, that's going to be the way that we actually purify our water, okay? So again, it's going to force it down, the solvent molecules are going to go into the beaker, and there it is. Just to give you an idea of what these look like and why they're not cost effective. They're very expensive. You only do this when you have no fresh water. Now, unfortunately, this is going to become quite prevalent to a lot of areas as the climate changes. A lot of these areas are finding less and less and less rainfall, and they're going to be forced towards these systems. Now, one of the reasons it costs so much is that the osmotic pressure of seawater, ocean water, is 27 atmospheres. So to perform reverse osmosis, they have to apply a tremendous amount of force, 50 to 60 atmospheres. That means everything that they use has to be able to handle those kind of pressures. Again, I encourage you to watch, you find a YouTube video that shows just 1 atmosphere and its effect on metal in metal cans, okay? So we're talking about tremendous amounts of pressure. So everything costs a lot more when you have to deal with these kind of safety hazards. So basically what happens is that you bring the salt water in from the ocean. It first goes through a pre-treatment. So just trying to get rid of all the big particles and anything that would clog up your semi-permeable membrane. It then goes into the reverse osmosis system. So you can see that the seawater comes in through the edges here, okay? It then passes through, so that it's coming from here, it's starting up to here, it passes through all these semi-permeable membranes. Notice there's a whole bunch of different types. So some are for cations, some are for anions, some are for big species, some are for organics. So it's got to go through all these different types of semi-permeable membranes. And then finally, there's a tube in the middle that has holes in it that allows that fresh water then to get into there, and it escapes. Now, the concentrated seawater, remember, as you're squeezing out the solvent, the solution is becoming more and more concentrated, which means its osmotic pressure is going to keep increasing to a point where it's just ineffective anymore. So they just pump out the concentrated seawater simply right back out into the ocean, okay? And then the fresh water coming from this inner tube is then going to go to a tank and eventually to your sink or shower, okay? Now, to give you an idea of the scale of these types of systems, this is one in California. There you can see the car right there, okay? These plants are absolutely immense to produce the amount of water, the amount of fresh water that we go through, okay? Each household goes through a tremendous amount of fresh water every day. It says a solution in which 2.24 grams of naphthalene, which is CaH10, and I'm going to call this NAP. Okay, so naphthalene in 40.9 grams of benzene, which has the formula C6H6. I'll just write that out, it's short enough. Has a vapor pressure of 83.2 torr. So now that's the vapor pressure of the solution, right? Is 83.2 torr. Again, a lot of times it is good to write down the values that you recognize using the variables that they belong to. That's going to make using the correct equation a lot easier. Okay, So again, this is why I stress you need to know what your variables are, because those are in your equations. If you know the variables that are represented by what's being said in the sentence, you're going to be able to understand what equations you need to use. Okay. Okay, so again, we have the mass of the naphthalene. So we have the mass of the naphthalene equal to 2.24 grams. And it wants us to determine the vapor pressure of pure benzene at the same temperature. So pure benzene now at the same temperature. So what are we looking for? Well, that would be this. Well, let's call this C6H6. So this is what we're looking for. Just a real quick side note. Does anybody know what naphthalene is? Most of you have probably never bought it, but I guarantee that your grandparents did. You ever hear of mothballs? Okay. So mothballs are these little white balls, and they have I can't describe the smell. It is very unique. If you've ever smelled them, you know what I'm talking about. I don't know how you would describe it. They're potent, they're very strong, and they basically keep moths away. I don't know if they kill them or the moths just can't stand the smell of them because they smell so bad. But again, they used to throw them. It used to be that our clothes were much less synthetic, and they were like pure cotton, pure wool. And in particular, moths love wool. That's like candy to them. And so if you stored your wool blankets and shirts and jackets, by the time you'd use them the next season, they'd be full of holes because the moths would come in and it's actually the larvae of the moth would come in and eat them. And the mothballs prevented that. But anyway, so just reminiscing about being old. Okay, so now let's come back to this. So I want to determine the vapor pressure of pure benzene. So what am I going to do? How am I going to solve this? What equation am I going to use? There's other important wording that I did not read yet either.
Rowlett. I don't know how you pronounce it.
Raoul.
Raoul's law.
Okay. 4. There's 2 Raoul's law.
Oh. The wait, hold on. Yeah, it's a solid. So
Yeah, it's a solid and it's non-volatile. It tells you it's non-volatile.
So that, yeah.
Okay, so what is that equation then?
Well, the partial pressure of the solution is equal to the pure version of C6H6 times.
So that is the solvent, right?
Yeah, the solvent.
So it's a solution and then the solvent. And then go ahead.
And then times basically the mole fraction of the solvent.
Okay, now I'll make this a little bit more specific, right? So our solution is the naphthalene in benzene. So I'll just keep calling that the solution. The solvent is the benzene, right? So this was dissolved in this. So this is our solvent, and then that would be the mole fraction of the solvent. And I am looking for this, right? So I would simply rearrange this equation then. The vapor pressure of the pure solvent is then just going to be the vapor pressure of the solution. Divide both sides by the mole fraction of the solvent, benzene. Okay, so do I know the partial pressure of the solution?
Yes.
Yeah, it was given to us, right? So that's just 83.2 torr. How am I going to get the mole fraction of the benzene? Well, we've seen that already, right? So that's going to be the mole fraction of the benzene. Are going to be the moles of benzene over the total number of moles. So the moles of benzene plus the moles of our solute, which is the naphthalene, which I'm just going to write as nap. So now I got to get the moles of each. So the moles of benzene Well, they already gave us the mass of benzene, right? Or I'm sorry, they gave us the mass of benzene. So that was 40.9 grams of benzene. To get the moles, I'm just going to divide by the molar mass. So again, there's 6 carbon at 12.0107 grams per mole, plus the 6 times the 1.00794 grams per mole for the hydrogen. So that's going to give us then a molarity of 78.111 grams of benzene per mole of benzene. Which is going to give us then a total of 0.52326 moles of benzene. So this is what, 3 sig figs, so this will be 3. And then the moles of naphthalene, we're going to do the same thing. They gave us the mass of naphthalene is 2.24 grams. So that'll be the 2.24 grams of naphthalene. Again, naphthalene had the formula of C8H8, so that's 12.0107 grams per mole times 10 plus 8 times the 1.00794 grams for the hydrogen, giving you a molar mass of 128.17 grams of naphthalene for every 1 mole of naphthalene. The grams of naphthalene cancel, and that would give you then 0.017477 moles of naphthalene, 3 sig figs. So now we can plug that all into here. So the moles of benzene we just determined to be 0.52331 moles. I'm going to ignore these now because we know that this is going to end up being unitless. So again, now it's the moles again of our solvent plus the moles of our solute. Mixed operations, so this plus this is actually going to be equal to 0.54109 moles. So this is 1, 2, 3 passed. This is 1, 2, 3, 4 passed. So this can only be 3 passed. Now we're going to plug this into our calculator. So the moles are going to cancel. And that's going to give me a mole fraction of 0.9677. We have 3 sig figs. We have 3 sig figs. So this will be 3 sig figs. And then now we just put in 0.9677, and it's unitless, right? So remember, the mole fraction is dimensionless. The units cancel. Plug that into your calculator. That's going to give you 85.976 torr. We have 3 sig figs, 3 sig figs. So that's going to be 86.0 torr. So that is the vapor pressure of pure benzene at 23 degrees Celsius. Okay. Any questions about that guy? Homework problems? So number 38 from chapter 13 says, what is the melting point and the boiling point of an aqueous solution consisting of 0.086 molar sodium phosphate? Okay, so we're looking for the melting point. The melting point is the same as the freezing point. So that's normally called TF, or we could call it T fusion for melting. Okay, and then boiling point, you generally give the variable TB. Okay, now when we're, so how am I going to go about solving this problem? Taylor, what do you think? Let's start with the freezing point, or the melting point.
You're going to want to use the equation that has for the negative I KFCM.
Okay, so the change in the freezing point is going to be negative I KF, the freezing point depression constant, and then the concentration. What concentration is that? What unit? What type of concentration?
Molal.
Yeah, the mol, right? So this is a lowercase m for the mol. Okay, so that change then is going to be negative. What's the I going to be? Leah, what's the I going to be for this?
Three?
3. Okay, so I have sodium phosphate.
Yeah.
Now, is sodium phosphate a strong or weak electrolyte?
Strong.
Strong, right? So this is what it would look like in the molecular equation. Would say it was aqueous, right? But once we put that in water, which would make it aqueous, it's a strong electrolyte. And how would I write that? This is the molecular equation, and then the reality is in the complete ionic equation. What's it look like? How would I write it? If it was aqueous in the molecular equation, how do I write it in the complete ionic?
You break it apart, so it'd be I'm sorry. It'd be outer inner. Oh wait, yeah. Na3 plus PO4, but yeah. Why don't you just split it?
Okay, into what again?
Na3.
Where the 3 goes down here?
Oh, outside.
It's 3, right? We
Yeah,
don't know
yeah.
any polyatomic ions with sodium. What charge does it get?
Thinking. +1? Oh, but because it's 3.
1A,
Yeah.
so it's a +1. Metals are always cations, right? The metals are always cations and the non-metals are anions. So this is a positive and negatives, okay? So it's a +1, and we'd say it was aqueous. And then what about the PO4 part?
It was a part of that would be, wait, because it's PO4. Wouldn't it be -3 because of the?
Yep, right, because this is the phosphate.
I think I'm
4,3 minus aqueous, right?
Yeah.
Okay, so
Yeah. Oh wait,
so what is I then?
would it be 4? I'm sorry.
Yep.
Okay.
Okay, so yeah, there's 3 sodium and 1 phosphate. So this means I equals 4. Okay,
Yes.
so that
Okay,
means this is 4. Okay, Katrin, where am I going to get, what about this KF?
Isn't that something we'd have to look up?
Okay, so I'm going to look that up in a table. I'll find the freezing point depression constant table. And then when I look at that table, sorry, let me pull out the table. A lot of tables. Okay, so here would be the table. So what is that value then? There we go. So what is the value?
Would it be 1.86?
Yeah. Okay. Remember, it has nothing to do with the solute, just the solvent. Since this is an aqueous solution, our solvent is water, and we're looking for the freezing point depression constant, which is given in degrees Celsius per mol. And for water, it's 1.86. Now, since we're also going to be doing the boiling point, I'm going to get the boiling point while I'm here too at 0.512 degrees Celsius per mol. Okay, so again, you will always be given this table. I'm not expecting you to memorize any of these values, but you have to understand that it only has to do with the solvent. It has nothing to do with the solute, a colligative property. Okay. Okay, so now we have the Kf value then, so the freezing point depression constant at 1.86 degrees Celsius per mol. Whoops. Okay, 1.86 degrees Celsius per mol. And then finally, the mol concentration was already given to us as 0.086 mol. So we can see that the moles cancel, and I'm going to leave left with the degrees Celsius. And so that then is going to be equal to negative 0.6398 degrees Celsius. This number is exact, right? That's a counted number. It's going to break up into 4 particles. This has 3 sig figs. This has 2 sig figs. So this has 2 sig figs. And again, if you don't remember how to follow sig figs from Chem 110, you need to go back and learn how. Okay, there are rules that are posted on Canvas for you to follow. And again, all the homework solutions always follow sig figs. Okay. Okay, so now, Caitlin, what is the freezing point then of this this 0.086 mol sodium phosphate solution?
Because you would have to subtract it from 0, it would stay basically the same at negative 0.64.
Right, right, because we know that del T is equal to TF. Now, in this case, this is the final temperature, but it also, this is the final temperature, but it also represents the temperature of fusion of the new solution, right? And then Ti, this would have been the freezing point of the pure solution, pure solvent, in this case, water. And since we want TF, well, TF is just going to be del T. Now we're going to add Ti to both sides. And so that's just equal to our negative 0.638 degrees Celsius. And then plus the regular melting point is 0 degrees Celsius. We're going to consider this to be exact for water, but I listed in that table. So if you look at the table, I also list the boiling point and freezing point as well. So you'll notice I listed it as 0.000. So that would be to those 3 sig figs, right? Because again, zeros past the decimal point are always going to be significant. Normally that's in case, that's if there's another number. So if you have a non-zero number and a decimal point at any place, any zero past the non-zero number would be significant. That's a weird example because I wrote it as 0.000 degrees Celsius. That doesn't even make sense, but I just wanted to show you that we had it to 3 decimal places because we're always going to be using it for addition and subtraction, and that's where we're following the number of decimal places. Okay, so this is 2 past, so your answer would be 2 past, and so the freezing point of this solution then, we're going to round up. 1 past the last significant digit is 5 or greater. So we'll round up that last digit by 1 and then drop the rest of the insignificant digits. But remember, we're not going to round until we give our final answer. This is what I call an intermediate value. If you round intermediate values, your final answer is always going to be wrong. Okay, it's going to be off by 100th, 1,000th, 10 thousandths, I don't care. It's wrong. Go back and do the problem and don't round intermediate values. Okay. Okay. So any questions on that? Okay, then for the boiling point elevation, well, we're just going to use the equation for it. Del TB is equal to, this time it's positive, so there's no sign there because this is an elevation. We're going to be adding to that normal boiling point. It's going to be KB, not KF. And then again, the concentration in terms of Moel. Okay, so we already know that I is 4. KB we looked up at the same time that we looked up the freezing point depression constant and found that it was 0.512 degrees Celsius per Moel. And then again, the concentration was given to us as 0.086 Moel. So again, the Moels cancel. We end up with units of degrees Celsius. Plug that into your calculator and you're going to get 0.1761 degrees Celsius. Again, this is exact. This has 3 sig figs. This has 2, so the answer will have 2. So when we're multiplying and dividing, all we're looking for is the value with the fewest number of significant digits. So the measured value with the fewest number of significant digits. Now again, that was del T. We're looking for the final, which in this case is going to be equal to our TB.
Wait, I have a question real quick.
Yep.
How come for the number 4, like, would that be 1 significant figure?
No, that's exact.
Oh, okay.
Okay, how many fingers do I have?
5.
5. Is it maybe 5.2? No, as long as I don't hang around a nuclear power plant, we're going to be good, and I'm going to have 5 fingers. So counted numbers are exact.
Okay.
Okay, again, look at that. If you're unsure, look at the thing that I posted on Canvas about significant digits. It talks about what numbers are exact and what numbers aren't, and all that kind of stuff. Okay, so if you count them, they're going to be exact. If you have to measure it using a balance or a roller or some other device, then that's a measured value. Counted values are exact. Measured values have uncertainty. Okay. Okay, so in this case, this final temperature is actually going to be equal to the boiling point of our solution, right? So this is the new boiling point of the solution, that 0.086 Moel sodium phosphate aqueous solution. So that then means that this was our 0.1761, okay, to 2 sig figs. Okay, and Hannah, what's the boiling point of pure water?
The boiling point is 100 degrees Celsius.
Exactly. Now again, in this thing, I gave it to 3 decimal places. Okay, so we're going to say plus 100.000 degrees Celsius. So this is now, since we're adding and subtracting, so this will come out to be 100.1761 degrees Celsius. Now, since we're adding and or subtracting, we're looking for the measured value with the fewest number of significant digits. Now, this has 4 digits, but we put an underline there to indicate that only the second one was actually significant. So that has 2 significant decimal places. This has 3. So our answer can only have 2. 1 past that is 5 or greater, so we'll round up. And so it'll be 100.18 degrees Celsius would be the boiling point of our 0.086 molar sodium phosphate solution. Okay, any questions with any of that good stuff? Oh, by the way, before I forget, I posted a quiz. What do you need, Ann?
Why do you want to get back in the building? Isn't it
Do you have your key card?
I don't have it.
You don't, you have your ID. Your ID is your key card. If you can't get back in, come knock on my window and I'll come let you in.
I don't have my.
Yes, if you walk out, you're going to get locked up. So my students stole all my extra keys. So I never gave you a key?
No.
They stole them all. Okay, I'll give you my keys. You got to give them the keys back. That's the 3 is the outer doors, and then that's also the lab door, and then 2 is all the other doors. Okay. Okay, sorry about that. Okay. Okay, so I posted a quiz. I don't know if you've noticed it yet. It's called the submission quiz. You need to do those problems. More importantly than the problem itself is you being able to submit that quiz as a PDF, single file, not a whole bunch of JPEGs, a single PDF file uploaded through Canvas. Okay, you have till Monday to do that. You're allowed to do that quiz as many times as you want. So before each exam, I suggest that you just upload it. And I don't care if you upload now. For the first quiz, you need to upload it by Monday, and it actually needs to be completed as a real quiz, do the problems. After that, you can keep uploading whatever you want. Just make sure it's multiple pages, because that's where the difficulty comes in. I don't care if you upload pages of the newspaper just to figure out how to use Adobe Scan on your phone and to actually upload into Canvas, okay? So give yourself time. Unless you've done it before, there is a learning curve to it, okay? You can go online. There's plenty of videos that explain how to use it. Now, keep in mind, there's a version of Adobe Scan where you have to actually sign in and use their cloud, or there's another version, and these are all free, by the way, okay? There's another version where you don't need that. In the announcement, I put an icon of what the one that you don't need to sign into. So if you could find that app with that particular icon, to me, that's the easier one, unless you want to sign in. And then you could use the Adobe Cloud and that, but I don't know if you need to actually have, Penn State probably has that already. In fact, I know you do, you all have access to it, but I don't know if any of you have actually set it up. So again, if you use the one that with the icon that I showed, that's going to be the easiest one to use, okay? Okay, so again, make sure you take that quiz, and that's going to be due by Monday. Okay, let's try another problem. So it says, in order to determine, so this is number 44 from chapter 13. Again, these are the homework problems posted on Canvas. So it says, in order to determine the molar mass of a soluble unknown molecular compound, 24.3 milligrams, so this is our mass, 24.3 milligrams of the sample was dissolved in water to make 50 milliliters. So there is a volume of solution at 23.2 degrees Celsius, which would be a temperature. The osmotic pressure was measured as, so that is our osmotic pressure pi, is 44.67 millimeters of mercury at this temperature. So I want to know, what is the molar mass? So we're looking for the molar mass of the unknown compound. Again, I strongly encourage you to recognize the variable for each value that is given. That's going to make it a lot easier to solve these problems. You're going to know what equation you need to use. Okay, so Eugenie, what equation am I going to need to do this? You got to unmute your mic, hit spacebar. Nope, didn't work.
No.
There we go.
So pi equals IC times R times T.
I'm sorry, say it again.
Pi equals I times the molality.
The molality?
Molality, right?
Nope.
Molarity.
Molarity, big M, right? Capital M, big M.
Times R times T.
Okay. What is R? Because I know that's a constant. So which R are we going to have to use? There's two R's that you should know, right? The 0.082058 and the 8.3145.
0.082058.
Yeah, we got to use this one because the units are atmosphere, which would be our osmotic pressure, liter per Kelvin per mole, right? So there's our concentration and there's our pressure. And then that's the absolute temperature. So in this case, what am I going to solve for in this equation? Because I'm looking for the molar mass. What is the molar mass? If I was going to give molar mass an equation, what would that look like?
Like the numbers that are on the periodic table.
Okay, well, what units are they, though? What's the unit of a molar mass?
It's just grams.
Not just grams. That would just be a mass. This is a molar mass. So what's the unit's going to be? If it's a molar mass.
Grams per mole.
Yeah, right. And so it's going to be grams. What variable do we use for grams mass?
G.
Nope, that's the units. What variable do we use?
M.
M, right? We use M for mass. And what variable do we use for moles? Moles are the unit. What variable do we use for moles?
MOL.
No, that's the unit, mole. What is the variable? Just N.
Oh.
So there's our equation. So now I was already given the mass, right? So if I was going to say, I'd say, well, okay, that was 24.3 milligrams, but you already told me that molar mass has to be grams per mole. So I would need to convert that. So there's 1,000 milligrams in a gram, right? So that would give me my grams, but now I got to divide it by moles. So are there anything here that contains moles?
The molarity.
Yeah, right. So the molarity is moles per liter. So we know that if that is the molarity, so if the molarity is moles per liter, right, N over V, I would be solving for N. So N is equal to the volume times the molarity. Okay. So the volume was given to us as 50 milliliters. But I know that molarity has units of what? So this is the variable for molarity. What are the units for molarity?
Just CM.
Say again? Well, see, this is the variable. I agree with you. This, just M by itself, is a unit for molarity. But Jada, what does that big M represent in SI units?
Is it for the units for molarity?
This is molarity. What are its units? I mean, this is a unit itself. Big M is a unit, but it also represents something so that we don't have to write everything out. So what are the units for molarity?
I don't know that one. Sorry.
Keenan, what do you think? What are the units for molarity? Just hit your space bar.
Grams per liter.
No, that would be density.
Hold on. Didn't we already say it was just for molarity?
Molarity.
Molarity. So it's not moles per liter?
It is moles per liter.
Oh, I thought we already said that.
Nope, nobody said that.
Sorry.
Moles per liter, right? So that has units of moles per liter. So that means that this volume has got to be in liters. So I'm going to divide it by 1,000 since there's 1,000 milliliters in a liter. Now all I need is the molarity, and the molarity, of course, I can get from this equation. I'm just going to rearrange it for molarity. So that's just going to be that. The osmotic pressure was given to us as 44.67 millimeters of mercury. But I can see in the molar gas constant that has to be in atmospheres. So, Michael, how am I going to go from millimeters of mercury to atmospheres?
The same unit.
What, pardon me?
Are they the same unit, or is it the one where you got to go from 720?
Not 720,
Oh, shit.
760. Okay, so yeah, 1 millimeter of mercury equals 1 torr, but 760 millimeters of mercury equals 1 atmosphere. So 760 millimeters of mercury equals 1 atmosphere. And by the way, we consider this to be exact. Okay, so don't worry about sig figs here. Your sig figs are in the measured value. So now these millimeters of mercury cancel, and we have the units that we need. Okay. Okay. Taylor, what is the Van Hoff factor for this puppy? I.
Would it just be 1?
Yeah, why?
Well, the molecular compound is unknown.
Right, but it is a molecular compound.
Oh, yeah, so it's molecular, so it'd just be 1.
Right, so because it's a molecular compound, usually I equals 1. If I just tell you it's a molecular compound, you're going to assume that it's not a carboxylic acid, okay? And usually those carboxylic acids are so weak that it doesn't matter. They dissociate so little that it doesn't even affect the values to the number of sig figs that we're looking at. So molecular compound, we're saying I is equal to 1. So that I is equal to 1. Then we have R, which we already determined was 0.082058. Atmosphere, liter, per Kelvin, per mole. And then the temperature. Okay, Leah, what do I got to do with the temperature?
You gotta change it to Kelvin.
Right, and how do I do that?
You plus 273.15. Yes.
Kelvin, right? Now this is going to take it to 1 past, so we have an intermediate step here. And so you'd need to plug this into your calculator, and this would be equal to 273. I'm sorry, no. Okay, the solutions manual is wrong. So 296.35. And this is 1 past, this is 2 past, so this would be 1 past. So now we've gone up to 4 sig figs there. You would plug that into your calculator, and you would then get the molar concentration of, let's see, 2.41699 times 10 to the negative 3. And for units, well, let's see, our atmospheres canceled, our Kelvin per Kelvin cancels. Now I have a per mole, which means that's actually in the numerator, right? So that's going to be moles per liter. So that's exactly what I wanted, moles per liter. Okay. Now I could plug that into here to finish getting my number of moles, right? We're trying to get the number of moles. We already multiplied it by the volume. Now we want to multiply it by the molarity that we just determined. So 2.41699. Whoops, and this was to what? So that's 4 sig figs, that's 5 sig figs, that's 4 sig figs. So this is actually 4 sig figs times 10 to the minus 3 moles per liter. We can see now that the liters cancel, and that gives us moles, and so that is equal to 1.20849 times 10 to the negative 4 moles. So that's, let's see, 4 sig figs, exact 4 sig figs. So that's 4 sig figs. So that puts it there. So now we know the mass, and the number of moles within that mass is this number of moles, 1.20849 to 4 sig figs times 10 to the negative 4 moles. So now I have units of grams per mole, exactly what I expect for a molar mass. Plug that into your calculator, and you're going to get 201.07 grams per mole. I have 3 sig figs, exact 4 sig figs, so this will be 3 sig figs. So your answer would be 201. Again, this next number is less than 5, so we just drop those insignificant digits, and it would be grams per mole. Okay. Any questions about that?